Hello students, today I am going to solve some more numericals on heat exchangers. Here the first one is that engine oil is to be cooled from 80 degrees Celsius to 50 degrees Celsius. Okay, here engine oil is to be cooled by using a single pass counterflow concentric tube heat exchanger. Here it is a double pipe heat exchanger and it is a counterflow with cooling water available at 20 degrees Celsius. Okay, here the 20 degrees Celsius is the inlet temperature of the cooling water. There is a cold fluid inlet temperature. And water flows inside a tube with an internal diameter of 2.5 centimeter. Inside the tube, water flows with a flow rate of 0.08 kg per second. The flow rate of the water is given. And oil flows through the annulus at a rate of 0.16 kg per second. Oil is flowing with a rate of 0.16 kg per second. The heat transfer coefficient for the water side and oil side are the inside heat transfer coefficient and outside heat transfer coefficients are 1000 watt per meter square degree Celsius and 80 watt per meter square degree Celsius respectively. The following factors are 0.00018 meter square degree Celsius per watt for water and oil side. Okay, for water and the oil. The tube wall resistance is negligible. Okay, the tube wall resistance, the thermal conductivity of the tube wall is negligible. Calculate the tube length required. The tube length required we have to find out. For that, take CPW is equal to 4180 joule per kg Kelvin and CP oil is equal to 2090 joule per kg Kelvin. Here the counterflow heat exchanger that we have to draw, and here the inlet temperature of the cold fluid only given and inlet outlet temperature of the hot fluids are given, and we can calculate the outlet temperature of the water by using the mass flow rate and specific heat. Both are given for both the fluids. Here the THI and TH0, the oil is flowing in this direction, the water is flowing in this direction, its temperature is increasing. Okay, not this one, this is the TC0, and here the temperature of the cold fluid is increasing. And here the energy equation directly, if you take the Q, rate of heat transfer, is equal to mH Cph THI minus TH0, that is the heat lost by the hot fluid, that is equal to mC Cpc Tc0 minus Tci, that is the heat gained by the cold fluid. And Q is equal to 0.16 is the mass flow rate of the hot fluid. It is a 2090 specific heat, 80 temperature, 80 minus 50. Its inlet temperature and outlet temperature of the hot fluid are known. Okay, then 0.08 it is a cold fluid flow rate, 4180 is a specific heat of the water, Tc0 is unknown and its inlet temperature is given, Tci 20. And from this one, by simplification from these two equations, we are going to get that is Tc0 is equal to 50 degrees Celsius. And Q for this equation, if we calculate the Q, we are going to get 10,032 watt. In this case, we can see that one mH Cph is equal to mC Cpc. Okay, both are equal. Then here the Ch is equal to Cc. Then whatever the Ch is equal to Cc, whatever is there, then Cc, the heat capacity rate of the both fluids are same. Then whatever the temperature difference is there, it remains constant throughout the heat exchanger. Delta T remains throughout the heat exchanger. Therefore, delta Ti is equal to delta T0 or a delta TL. Delta T0 is equal to delta TL. Already we know that if the delta Ti is equal to delta TL, Ta0, then we can write that one, whatever this delta T LMTD is there, any one temperature difference that we have to take. That is the delta T0 is equal to delta TL. Okay, that is the THI minus TA. C0 is equal to H0 minus TCI, that is equal to 30 degrees Celsius. Therefore, LMTD is equal to 30 degrees Celsius. First we can calculate. Then overall heat transfer coefficient based on the inside surface area will take. Okay, that is because of inside's diameter we know, the AI also we can have from that one. That's why 1 by HW plus of directly that whatever the fouling factors are there, those are to be added. That is FW plus of F0, that is a fouling factor of water side and fouling factor of oil side, plus of 1 by H0 oil side heat transfer coefficient. If you add all these things, we are going to get the overall heat transfer coefficient as 72.15 watt per meter square degree Celsius. Then LMTD already we have. Then Q is equal to UI LMTD. Then AI whatever is there, that we can find out. AI is equal to Q by U LMTD. That is this Q already know, U know, LMTD we know, area we are going to get. From this one area, the diameter already we know that one 2.5 centimeter. Then length of the heat exchanger we can have. AI by pi di, that is equal to area, pi into di, that is diameter is given. Then it is a 59 meter of the length. The another numerical, that is a tubular heat exchanger consists of 200 tubes. Tubular heat exchanger consists of 200 tubes, each 20 mm outer dia and 5 meter length. Hot fluids flow inside the tube and cold fluid flows over it, but in opposite direction. That means it is a counter flow heat exchanger. The overall heat transfer coefficient based on outside diameter is 320 watt per meter square degree Kelvin. Determine outlet temperature of both fluids and total transfer using data given below. That means the total heat transfer using data given below. Okay, heat transfer we have to, that is the total heat transfer, that is a Q we have to find out. Actually it is in the numerical, that in the question paper is a total transfer it is given, but it is a total heat transfer. Then THI is given 120 degrees Celsius, TCI is given. Inlet temperatures of both the fluids are given. The mass flow rate also given. Specific heats also given. Okay, and here what is asked, that one, it is outlet temperatures of the both the fluids are asked. Already we know that if the outlet temperatures are not known, are not easily calculated, then we have to go for the NTU effectiveness method. For that, the first thing we have to do that one, okay, the area which is required, that is taken here for the 200 numbers of the tubes. The total heat transfer surface area, the total heat transfer is asked, not only single pipe, for 200 tubes the total heat transfer. That's why this A0 we have to take for the 200 tubes. Okay, that is pi d naught L, length 200, that is goes the total outside area, because U0 is their total outside area, because that one U0 into U0 area, U0 based on that one A0 outside area, surface area we have to take into consideration. The first thing in this one, that is we have to take, that is the capacity rates we have to take, that is MH CPH is equal to CH, that is 40,000, and CC is equal to MC CPC, that is 5 into 4,000, that is 20,000. Then C mean is CC and C max is CH. Then C mean by C max is equal to 0.5. NTU is equal to U0 A0 by C mean, that is 320 to 62.83 by 20,000. That 1.0053 we are going to get. Then for counter flow heat exchanger, already we know this one from the data handbook also we can take. This is effectiveness for the counter flow heat exchanger, 1 minus exponential minus n 1 minus c by 1 minus c into exponential minus n 1 minus c. This we are going to take this equation, that is this one equation we have taken. In this one n we have to substitute, okay, then c we have to substitute. By substituting this one and after calculation we are going to get this effectiveness equation. And for calculation of the temperature, we already know that one, we have to use the effectiveness equation which will be in terms of the temperatures. That is, effectiveness is equal to CH into THI minus H0 by C mean THI minus TCI. That is actually transfer to the maximum possible heat transfer. That can be given for the cold fluid also. That is Cc into Tc naught minus Tci by C min into Thi minus Tci. By substituting this effectiveness in this effectiveness equation in terms of the temperatures, Th naught we can find out 91.7 degrees Celsius, outlet temperature of the hot fluid. Then if you substitute the effectiveness in this equation, second equation, that is 0.56 into 1, Cc is 1, Cc by C min is 1, as Cc only C min, Tc naught minus 20 by 120 minus of the 20. Then this we can get as a 76.6 degrees Celsius outlet temperature of the cold fluid. Okay, like this the different numericals we can find out, solve by using this one. There are some few numericals on the mixed flow heat exchanger I am going to discuss. Okay, there we have to use, that is mixed flow, cross flow heat exchanger. In that cross flow heat exchangers we have to use that whatever the this counter flow heat exchanger LMTD only, and from that we have to take the correction factor. Then correction factor if you take by taking that corrected heat transfer, corrected the LMTD we have to find, then corrected LMTD we have to substitute to find the heat transfer or anything. Okay, that is one. This is cross flow heat exchanger. A cross flow heat exchanger in which both fluids are unmixed is used to heat water with an oil. Okay, this water oil enters at 30 degrees Celsius and leaves at 85 degrees Celsius at a rate of 1.5 kg per second, which will this I will continue in the next class. This one oil with the Cp is equal to 2.3 kJ per kg Kelvin enters at 120 degrees Celsius with a mass flow rate of 3.5 kg per second. Take A is equal to 30 meters square. Calculate the overall heat transfer coefficient by using the LMTD method. Okay, overall heat transfer coefficient we have to find out. Then first thing, the given data, mass flow rate of the cold fluid 1.5 kg per second, the Cpn, that is Cpc cold fluid Cp, and mass flow rate of the hot fluid Mh 3.5, Cph is 2.3 kJ per kg Kelvin. Then Thi we are having, Th naught we have to find out. Then Tci, Tc naught we know, and this Th naught we can calculate easily. That is by using the energy equation. Already we know that Q is equal to Ch Thi minus Th naught, Cc is equal to Tc naught minus Tci. Then Q is equal to 1.5 into 4.187 into 85 minus 30. That Q we can have. This is 345.43. Then that can be equated with the cold fluid, that is Cc into 120 minus Th naught. Okay, then Th naught we are going to get as 77.09 degrees Celsius. Now for the cross flow heat exchanger, both fluids unmixed, we have to use the LMTD for the of a counter flow heat exchanger with a correction factor Fc, and this correction factor we can find out from the data handbook. Here the P we have to take Tc naught minus Tci by Thi minus Tci. R is equal to this one. On the graph we have to plot, and for that we are going to get the Fc, correction factor. Then the LMTD for the cross flow heat exchanger is equal to LMTD for counter flow and that correction factor. Then here P we are going to get as a 0.61, R is equal to that we got this 0.78, and from that Fc from the data handbook we are going to get the, from the data handbook of the double pipe heat exchanger. From that, for that I will tell you page number. Page number 152. Here single pass cross flow both fluids unmixed is the third chart. There R we have to P we have to locate along the x-axis and R on the curve we have to locate. Then F correction factor we will get that one. Okay, after getting the correction factor, LMTD for the counterflow we have to take. The LMTD for the counterflow, it is the same equation, delta T naught minus delta TL by ln of delta T naught by delta TL. LMTD, this is for the counterflow heat exchanger. Then LMTD for the cross flow heat exchanger, FC into LMTD for the counterflow heat exchanger. This 0.88 into 40.746, that is equal to 35.86 we are going to get. Then by using that in the heat transfer equation, U A LMTD, then Q by U overall heat transfer coefficient we have to find, then Q by A LMTD. Already area given, Q we have calculated, then LMTD just now we have, then overall heat transfer this will get. Okay, this I will stop here and I will continue this